When we think about fluids, we start by thinking about pressure. Pressure is a useful idea when there's a force spread out over a surface area, not just a force applied to one little lump of mass, but force spread out. And for example, here at the bottom of a pool, you've got a force on the bottom equal to the total weight of all the water above, but that force is spread out over the whole area of the bottom of the pool. Pressure is just a ratio of force per area, the number of newtons of force in 1 square meter of area. And let's look specifically about the force that's caused by the liquid in here. So we go down to some depth below the surface, d meters, and imagine a little patch of area, a horizontal patch of area of a square meters, d meters below the surface. What's the force on that little patch of area? The force is equal to the weight of all the water directly above it, plus the weight of all the air above that. And the grand total weight of all the matter directly above that surface area, water and air. So, total force on that area is the weight of the water plus the weight of the atmosphere, all pushing down on that surface area. Pressure on that little bit of surface is just that weight divided by the area. And since the total weight is the weight of water plus weight of the atmosphere, then the pressure is just weight of the water divided by area and weight of the atmosphere divided by area. Remember, weight is mass times g, mass times 9.8, the acceleration due to gravity. And whenever we're dealing with fluids, it's very often going to be useful to think of mass in terms of density and volume. Density, remember, is the number of kilograms of mass in 1 cubic meter of volume. And so we could write mass as just density times volume. And that's what I do here. The total pressure is the weight of the water divided by the area. Weight is mass times g, and I'm writing mass as density times volume. Density times volume, that's mass times g. Mass times g, that's weight. Meanwhile, the force from the atmosphere pushing down divided by area, we'll just refer to that as the pressure caused by the atmosphere, the pressure caused by the weight of all the atmosphere that's directly above this area. So, density times volume times g, density times depth times area, d times a, depth times area, that's the volume. This surface area times the height, d. And then plus atmospheric pressure. Well, look at what we have here. An area factor and then an area factor in the denominator, they cancel out. So this factor here, which is what? It's weight of the water divided by area. In other words, the pressure caused by the water. Force over area, that's pressure. Since these a's cancel out, the pressure due to the water is just density g depth. And then atmospheric pressure. So now this is the total pressure on this this area here due to the weight of everything that's above it, the water and the air. If we're interested only in the pressure due to the fluid and not the atmospheric pressure above and beyond that, it's an even simpler expression. Pressure, when you're at some depth, d, below the surface of some fluid, is just the density of that fluid. And in this case, we were thinking of a pool full of water, but all this stuff works no matter what kind of fluid you're using, times g times the depth. The important thing to notice here is that the pressure due to how deep you are in the fluid depends only on the depth. It doesn't depend on the grand total volume of water you have. For example, let's say you've got a big pool here. Say it's 10 meters deep. And then got a little tube here, vertical tube filled with water. Tube is 10 meters long. So they're both filled with water, both filled with the same substance. So for both of these things, that factor is the same. And for both of these things, the depth below the surface, here's the surface, and if we go to the bottom of each of these things, bottom of the pool, bottom of the tube, the depth below the surface is the same, 10 meters. So the pressure here at the bottom, due to the water above, is the same as the pressure here, even though the volume of water here is much, 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 much bigger. And the volume here is really tiny, because pressure depends on just depth, not on the volume of water. And that, of course, is how a municipal water tower works. The water tower gives pressure to all the water coming out of all the water that comes out of the shower heads and sinks, just by being elevated. Here's the water tower. And then tube that connects the water in the water tower to wherever it's going to go in the town. And let's say this is filled, the tower is filled up with water up to the top here. So you now have water pressure here that depends only on how far below the top of the water level this point is. It's not exposed to the atmosphere, so there's no additional pressure from the weight of the air above. The pressure here is just due to the depth below the top of the water level, because that's all the pressure, the fluid pressure depends on. Does not depend on the total volume of water. So you don't need a large volume of water in the water tower in order to create pressure for the town. You just need it to be high above the rest of the town. And the higher it is, the higher the pressure you'll get for the town. You wouldn't increase the pressure at all by having a bigger volume tank here at this same elevation. You could increase the pressure by taking that same amount of water and lifting it higher. Well, let's look at an example of using this. Let's say we have some cylinders full of water, 4 of them. And the height of this first one is 40 centimeters. And the height of this second one is 30 centimeters. And then the height of the next one is 35 centimeters. And then the height of the last one here is 45 centimeters. And let's say that now they're filled with different types of fluid. Different fluids will have different densities. So let's say the fluid here has a density that we'll call a 0.9 times 10 to the 3 kilograms per cubic meter. The density of plain old water is 1 times 10 to the 3 kilograms per cubic meter. And let's say the density of B, is, let's say, 1.3 times 10 to the 3 kilograms per cubic meter. And the density of C is just plain old 1 times 10 to the 3 kilograms per cubic meter. Got water in this one. And in D, the density will be 0.8. .8 kilograms per cubic meter. So, what's the fluid pressure at the bottom of each cylinder? Well, the pressure contributed by all the fluid, by all the liquid above the bottom of the cylinder is just density G depth. That, of course, is the same factor for all 4. It's 9.8 meters per second. Density and depth are the only factors that matter, the only factors that could cause there to be different fluid pressures. So ranking just by the product of density times depth is really the same as ranking by fluid pressure itself. And that's how we can rank these 4 cylinders from greatest to least in terms of the fluid pressure at the bottom. So fluid pressure A we're just taking depth times density, because that's the product of those two things is the only thing that will differ from one fluid to another. And so this is 40 centimeters or 0.4 meters. 0.4 times 0.9 times 10 to the 3. Gives us 0.36 times 10 to the 3. And then for B, density times depth is 1.3 times 10 to the 3 times 0.3 meters. So 0.3 meters times 1.3 times 10 to the 3 gives us 3.9 times 10 to the 3, or sorry, 0.39 times 10 to the 3, 0.39 times 10 to the 3. So a little bit larger than case A. And then C, density times depth is 0.35 centimeters, 0.35 meters, 35 centimeters, times a density of 1 times 10 to the 3. So that gives us 0.35 times 10 to the 3. And then D, the product of density and depth, is 0.8 times 10 to the 3 times 0.45 meters. So 0.45 meters times 0.8 times 10 to the 3 gives us again 0.36 times 10 to the 3. So if we're ranking those 4 cylinders in terms of fluid pressure at the bottom, the ranking comes out this way. The biggest pressure is B. And then biggest pressure is B. And then the next largest pressures are both A and D. They're both 0.36. And the smallest pressure then is C, 0.35. So that's how fluid pressure works. For any one fluid, pressure depends only on depth. And if you're comparing different fluids, like in this example, pressure depends only on the density of the fluid and the depth.